finally arrive at the part of our implementation plan that allows us to verify and tune IPsec VPNs and verify the service complies with our routing and addressing capabilities at the branch router. Our security support team has verified and confirmed the configuration is complete on both the headquarters and branch routers. It is our job to verify this configuration works smoothly and that all services remain consistent across the VPN tunnel. The services we need to verify are within the context of the previous lesson. In other words, static routing and routing in general, and network address translation. As you look at the topology diagram in the top left panel, our job is to verify the VPN is established and working as a backup of the private WAN in preparation for the next step, which is decommissioning the WAN and using the IPsec VPN tunnel only. Remember the implications of IPsec VPNs on all of the services we configured. Let's focus on the features of IPsec and the functions we discussed in previous lessons. In the top right panel, we can see the IPsec VPN toolkit we used, with a couple of commands. Show Crypto Map allows us to display the main components of our IPsec VPN configuration, including the interface where the crypto map is attached and the crypto ACL. The Show Crypto Session Detail displays additional information on the status of the tunnel once it is established. We use Show Crypto Map in our branch router, and we can see a crypto map called VPN. You can quickly determine that this is associated with the internet-facing interface. Amongst other things, we can verify the peer settings are correct, that it is in fact our headquarters router on its public-facing interface. We also verify the existence of our crypto ACL, which defines the type of traffic that will be encrypted and tunneled across to the other side. One of the main tasks in this type of verification is making sure the other side, the headquarters router, has a mirror image configuration. Let's go there. We see the interface pointing to the private WAN going up and down because of our testing. Let's display the crypto map. You can see we have a similarly named crypto map, VPN. Our peer is the branch router. The ACL, and this is very important, is the mirror image of the other. This time we are tunneling and encrypting traffic that matches a source on the headquarters LAN and a destination on the branch office LAN. Keep this in mind as we go through our testing and verification. You can also see the interface where this is attached. Before we start testing, let's make sure all of our components are there. We will go through testing similar to the previous lesson. Let's bring down the private WAN and make sure the backup connection is triggered, going through the tunnel and into the private LAN on the other side. Before we do that, we'll use a debug command. Very dangerous in production environments, but it will do for the purposes of testing. Debug crypto IPsec. The objective is to see the tunnel is being triggered when we reroute traffic through the internet connection. If we use show IP route, we should be routing things through the private WAN. We are doing that. We see the default route going through the EIGRP network. If we trace a private network or private interface, like 10.2.2.2 on the headquarters site, and source it on our LAN interface, this is LAN-to-LAN traffic. We see we are going through the private network. Let's bring down the interface pointed to the private WAN. And try again. We try our trace and source it at the LAN interface. Something is wrong here. This appears to be going through the correct interface across the service provider and into the internet connection. But it's seeing a host unreachable indication coming back from the trace output. We are tracing from the source LAN into the destination LAN, and that should and does match the crypto map. And the crypto ACL from 10.1.1 to 10.2.2. What's going on here? We should see traffic go to the internet-facing interface, find the crypto map there, match the crypto ACL, and trigger the tunnel. However, we didn't see any output of our debug IPsec command. Remember, we are running and deploying NAT in the branch router. Our NAT definition, if we go back to it and show IP NAT statistics, it is matching and translating some traffic. Here's what's happening. The traffic that matches NAT is defined by the NAT ACL. Let's display the NAT ACL. Notice that it matches any traffic coming from 10.1.1. That's our trace. We sourced it on 10.1.1. The traffic will be translated, and then it will not match our crypto ACL. Here's proof. If I use show IP NAT translations, I see a host of translations on the 10.1.1 traffic, which is IPsec traffic trying to go out. It's translated to 192.168.250.18 in this example. That does not match our crypto ACL. Remember, we debugged crypto IPsec and saw nothing, so it's not even triggering the tunnel. As you look at the top right panel, we permitted every security control and filter on this interface. Let's use show IP interface on serial 0/0/0, which is our internet-facing interface on the branch router. Let's verify the Internet Inbound Access List is allowing IPsec. We already did this. As a way of refreshing this information, we can use show IP access lists Internet Inbound. We see the first three lines are the way we configured them in the previous lesson. It is allowing all protocols that pertain and relate to IPsec. We will go through similar testing to that of the previous lesson, shutting down the private WAN and verifying the traffic is rerouted, this time into the VPN tunnel and over to the private LAN of the headquarters router. Before we do that, we will debug crypto IPsec, which will be helpful for the purposes of our demonstration. It will show that the tunnel is being triggered. Right now, if we trace the remote destination 10.2.2.2 and source it on our own LAN, this should be traffic that is going to cross the private WAN right now, and it does. Now, if we shut down the interface, and our EIGRP peer goes down. If we repeat the trace, we should be rerouted into the VPN. Let's do that. Trace 10.2.2.2, source it at 10.1.1.1. Look at that. This is strange. It looks like we are taking the internet route. That traffic should be sent to the interface where the crypto map is attached. It should match our crypto ACL, and it should be encrypted. However, we are seeing a host unreachable indication in the output of our trace. What is going on here? Remember, we are deploying NAT in this branch router. If we go back to our NAT definition, which we can see with show IP NAT statistics, we can see what's going on. The access list that defines the traffic to translate is NAT-ACL. If we display the NAT-ACL, we can see this definition matches traffic sourced at our LAN 10.1.1.1. That is our trace. We were sourcing it at our LAN interface. It matches the ACL definition and is therefore being translated into our address pool. We can prove that using show IP NAT translations, which shows a host of NAT translations for 10.1.1.1. That shows IPsec traffic trying to go out, but then it's being translated into 192.168.250.18. And that does not match if we display the crypto map again. That will not match our definition of traffic that goes through the tunnel. What we're seeing is what we discussed in our IPsec lesson. If you look at the top right panel, you can see that the impact of IPsec, or one of them, is on NAT. Remember, IPsec traffic will remain private across the tunnel. The traffic coming from the host on the right side, in this example, will be encapsulated as it reaches the tunnel, which is the router on the right. That traffic remains private, with private addresses. The public addresses are set in the outer packet, the IPsec packet that will traverse the public network. When it reaches the other side, decapsulation recovers the original packet and forwards it to the destination. That is all based on the encapsulation capabilities of IPsec. Right now, the packets sourced at our LAN are going out translated into something else. By not matching the crypto ACL, it's not encrypted. It goes out in clear text, with a destination of 10.2.2.2. That destination is not valid in a public network. It is private. That's the reason we see a host unreachable message. The solution is to do NAT exemption. Using this technique, you will prevent traffic that needs to go through the tunnel from being translated by NAT. Again, if our NAT definition is done according to the NAT ACL, all we have to do is change the ACL to deny the traffic we're trying to exempt. Here's how it goes. You would config T, then create the entry of the NAT ACL that denies traffic sourced at our branch LAN and destined to the headquarters LAN. The traffic will not be translated. Then it will encounter our crypto map, match the crypto ACL, and go through the tunnel. Here's how the ACL looks in the end. Show IP access list NAT ACL. It is denying the VPN traffic and permitting all other traffic sourced at the local LAN and going to any destination. That would be internet traffic that needs to be translated. Let's try to reach the remote destination now. I'm going to try ping first and not trace. I'll explain why in a moment. We'll ping the remote LAN destination and source it in our local LAN. That should match the crypto ACL and go through the tunnel. Let's try that. Look at that. The output of the debug command for IPsec is fairly verbose. We're going to undebug that, but it does display the things we saw in our initial IPsec lesson. It is establishing the tunnel between our local branch router and the headquarters router. The traffic actually triggering the tunnel is traffic going from one LAN to the other. That is the traffic that's being encapsulated. If we go back in the top right panel to our crypto commands and the IPsec commands, we can display the crypto session detail command. we can see an established session is up toward our headquarters peer. Here's the IPsec flow that triggered the tunnel. You can see that we are encrypting and decrypting packets toward the tunnel. This is proof the tunnel is established. In fact, if I ping again, I should see the packet counters increase. We see 5 ICMP echoes. That means 5 more encrypted packets, to make 9 total. What happens with trace? The trace example is a very good example of how services and addressing needs to be aligned with crypto-ACL. At least, you need to be aware of which traffic is being encrypted and tunneled by the IPsec VPN. Look at this. If we trace the remote destination and source it at 10.1.1.1, this is not showing anything. It is failing. The trace is not coming back. Let's see why. If we again display the details of our crypto session, we see that it encrypted a series of packets, but none of them came back to be decrypted. Let's go ahead and see what the headquarters router is saying. We can see all of the commands saying the interface has been going down. But if we display the crypto session detail on the router, we can see that similarly, a series of packets has been decrypted, so they have reached the headquarters router through the tunnel, but a lot fewer have been encrypted back into the tunnel. Let's use debug IP packet. I'm going to use that command, knowing it's pretty dangerous in a production environment. Let's trace now and try to learn something from this. We'll trace again from the branch router. We see that it continues to fail. We stop the trace and go to the headquarters router. Let's undebug to get rid of the clutter. We can see the router is sending packets back to 10.1.1.1. But those packets are sourced at 192.168.2.2. Here's an incoming packet destined to 10.2.2.2. But the return is going back from the router, 192.168.2.2. This doesn't match the crypto ACL here. We can display it again. This is matching, or trying to match, packets going from one LAN to the other, but not from 192.168.2.2, the way it's showing in the debug. There's a good reason for this. Remember, the trace command sends UDP packets with a high port number. That's the way Cisco IOS does it. The way trace works is by having routers send back ICMP messages of port unreachable back to the source. It is the router that sends the message back and not the intended destination, in this example 10.2.2.2. Because of this, trace doesn't work because the router tries to send the message back, but the message does not match the VPN definition of the crypto ACL. Therefore, it goes out in the clear to the destination 10.1.1.1, which makes no sense in a public network. What's the solution to this? We can change the crypto maps. This is a good example of how everything that needs to go through the tunnel needs to match the crypto ACL. Let's display the crypto map again. The crypto ACL is called VPN ACL. All we need to do is add the definition of the traffic we're trying to encrypt, those ICMP messages back from the router, to the crypto ACL. Let's do that. If I use Show IP Access Lists for the crypto ACL, Extended VPN ACL, verifying that's the name of the ACL, we can add a permit statement that permits ICMP traffic coming from the host 192.168.2.2 to the destination, anything on the 10.1.1.0 subnet. Remember, there must be a mirror image on the other side. We go back to the branch router, configure our access list, and create a mirror entry, permit ICMP coming from this side of the network going to host 192.168.2.2. Let's try our trace now and see if it works. Repeat our trace going to 10.2.2.2. Actually, let's undebug everything, just in case we had any IPsec debug enabled. We now trace 10.2.2.2, source it from our LAN interface. That should match the tunnel going outbound. Now we're seeing the trace works, and there's only one hop into the destination 10.2.2.2. It's all a matter of having traffic match your crypto ACL if you want it to go through the tunnel. NAT exemption is very important, and this shows the links and dependencies between your VPNs and regular services such as routing and NAT. Speaking of routing, this is another issue and impact of IPsec in branch connectivity, as you can see in the top right panel. We're going to fix this problem in our next lesson, but remember, IPsec can only tunnel unicast traffic. If we wanted to continue our migration into an IPsec VPN-only scenario for this branch, we would not be able to run EIGRP across the VPN. We will be able to resolve the problem with GRE tunnels in our next lesson. In this lesson, we learned a few things. We demonstrated there are dependencies between services at the branch router and a potential IPsec VPN connectivity option, a clear trend in branch connectivity. We were able to verify and tune the IPsec VPN, verify it works, and tune the NAT service around it, so the tuned-up tunnel works smoothly and our services are aligned with the connectivity option. We will now move on to a lesson where we create GRE tunnels.